Okay, this lesson is going to be a lot of notes for you guys. I'm sorry. This lesson's about periodic table notation, or how we represent ideas on the periodic table. There is a homework associated with it, which we will do in class. You could, if you wanted to, go ahead and copy down this heading into your classwork section of your binder, and we'll do this when we see each other. And we have a quiz that accompanies this lesson. So it's going to be based on everything you've learned up to this point, not including this lesson. So be prepared for that quiz as well when I see you guys next. Definitely, in the do now section, or in the classwork section of your binder, copy down this do now. In this do now, you're going to just copy down all these questions. You can definitely shorten this question if you'd like to, and we'll answer all four of them in class. All right, so I'm going to start you out with some note taking. So what's the nuclear charge of the element in the key? So nuclear charge, by the way, is the charge of the nucleus. I'll write that in for you now. So it's the charge of the nucleus, and the nucleus has certain particles in it. From the last lesson, you should remember that it has protons and neutrons in it. Neutrons don't have a charge. Therefore, the charge of the nucleus is really just equal to the number of protons. So if that's true, if it's equal to the number of protons, and the number of protons, which we've learned at this point, is the atomic number, or it's 6, then the nuclear charge of the element in the key is going to be positive 6. Now I chose to put a positive there because positive is the charge that protons have, and protons are what give elements their nuclear charge. Okay, so a list of elements and their corresponding symbols. You should have a reference table by now. You should have printed the one you looked up, or I've given you one. And the list that you're looking for is table S. It's a very long list at the end of your reference table, and you can use it to answer questions like A through D. So find your table S and try to figure out these answers before I even write them in. But the element Pb you can find on table S as lead. I believe it's element number 80-something, 82 or 83. What is the symbol for chlorine? So when you look up chlorine on table S, you'll also find its symbol, Cl. I want to point out these two questions are really helpful for all of you because you guys are just starting out in chemistry. So you don't automatically know that the name for the symbol Pb is lead, and you don't automatically know that the symbol Cl goes with the element chlorine. I mean, I know that, but I've been doing chemistry for years, and you guys are going to really need to use table S a lot at the beginning. So symbol for gold is going to be Au, and the element name for the symbol Ag is going to be silver. All right, so one thing, I don't know if you picked up on this, but I did it on purpose, is lead starts with a lowercase l. Silver I started with a lowercase s. A lot of people have the instinct to capitalize the names of elements, so they'll put capital L, capital S. That's actually incorrect. You should always use lowercase letters to begin the names of elements. I guess the only exception would be if you were starting a sentence with that element, but otherwise it's always lowercase. And the reason why the atomic number is in bold print on this answer key is mostly because the atomic number identifies the element. So since it identifies the element, we put it in bold because it's the most important piece of information for that element. So in the atom in the key on the previous page, that was carbon, and its atomic number was 6, and in this question it asks you how many electrons are in this atom, and in the previous lesson we found out that electrons should be equal to protons if the atom's neutral. So if the atom's neutral, it should be equal to the number of protons, which was 6, so my answer for this question would be 6. Why do you think the electron configuration is written as 2, 4? This is a reference to the orbits that atoms have that we talked about under the Bohr model. Under the Bohr model, we have orbit 1 and orbit 2, which is above orbit 1, and those different orbits have different numbers of electrons in them, and when we see the notation 2, 4, it's referring to the number of electrons in each orbit. So, in essence, orbit number 1 has 2 electrons and orbit number 2 has 4 electrons. A mass number is in some ways what it sounds like. It's a number that represents the mass of an atom. But its proper definition would be the sum of the quantity of protons and neutrons in an atom. So if you know how many protons an atom has by looking at its atomic number, and if you know the number of neutrons an atom has because of a statement in the question, for instance, you'd add those two things together. Let's say it has 6 protons and 6 neutrons. If that were the case, the mass number would be 12. So how can you determine the number of neutrons in an atom? Because if you want to find out the mass number, it's easy to look up the protons, but you can't just look up the neutrons. You have to figure out how many it is. The way that you can figure out how many neutrons an atom has is you need to start with a mass number. So you're given a mass number, and if you subtract from that the number of protons, you'll be getting the number of neutrons. So for those math geeks out there, the two equations that I just wrote down are actually the same equation. The first one says that the number of protons plus the number of neutrons is going to be equal to the mass number. The second one says the mass number minus the number of protons is equal to the number of neutrons. These two are the same equation. Basically, I've just rearranged them, isolating for different variables. But if you happen to be looking for the number of neutrons, just go ahead and take the mass number that's been given and subtract out the number of protons, which you can find on the periodic table. Here's an example. What would the number of neutrons be in a carbon-12 atom? So now you do need to know that C means carbon, and that 12 is a mass number. So you should add this to your Cornell notes, guys. Whenever you see a number following a dash that follows an element, so you see element dash number, this number is always, this number is always a mass number. And the mass number is protons plus neutrons. So what would the number of neutrons be? I'll do a quick calculation for you. Okay, so if the number of neutrons is the mass number minus the number of protons, and the mass number in this particular nuclide is a 12, then I'm going to start my calculation with 12 minus. So I'm just doing mass number minus, so that's this. I'm going to subtract from that the number of protons. So I need to know that carbon, its element is C, and you can look it up on your periodic table. Look for the bold number or the atomic number, which is the number of protons. And when you do look that up, you will find that for carbon, that value is 6. So that's the number of protons so far. So I've done that. And then I need to do that 12 minus 6, and I'll get 6. And this particular 6 is going to be the number of neutrons that the atom has. So basically, it has 6 neutrons, and it has 6 protons. You add those two together, 6 plus 6, and you get 12, which is the mass number. All right, so going further, atomic masses on your periodic tables are actually weighted averages of all the mass numbers of all the atoms of that type found in nature. This particular definition should be in your Cornell notes that just says atomic mass is a weighted average of all the mass numbers of all the atoms found in nature of that element. So weighted averages count some numbers more than others. Here's an example. So I have 3 particular atoms, and they all have an atomic number of 6. They do have different mass numbers, 12, 13, 14, and they have differences in their abundance. So 98% of atoms of the element have a mass number of 12, but 1% of atoms of that element have a mass number of 13, and 1% have a mass number of 14. I'm going to fill in some information to clarify some of this stuff. Firstly, it's that every one of these particular isotopes is carbon. And I know that for sure because all carbon atoms have the same atomic number, which is 6, and that's true for every element. Now, they do have different mass numbers, which also means they have different numbers of neutrons. You can do a quick calculation for neutrons, just like we did in the previous note, and it's going to be the mass number minus the atomic number. So in this first example, 12 minus 6 yields 6 neutrons. In the second example, 13 minus 6 yields 7 neutrons, and in the fourth example, 14 minus 6 yields 8 neutrons. So these three different isotopes have three different numbers of neutrons, 6, 7, and 8. So which of the possible mass numbers should contribute most to the average mass of the element with an atomic number of 6? So when I say atomic number of 6, I'm talking about carbon. And which of these three mass numbers should contribute the most? And it's going to be this one. And the reason is very simple. 98% of atoms of that element are mass number 12. So my note here is that since 98% of all carbon is carbon-12, then your answer should be carbon-12 because it's 98% of all carbon. So I've been using the word isotope sort of casually, hoping you wouldn't be panicked by it, but I need to give you a definition now. An isotope is a particular version of an element, like carbon, for instance, that has a particular mass number and a particular number of neutrons. And there are other isotopes of that element, usually. So in the example that we just did, I gave you 3 different isotopes of carbon. They all have the same atomic number, obviously, but they have different mass numbers, 12, 13, 14, which is because they have different numbers of neutrons. So when I define isotope, I'll just think of it as a version of an element with a particular number of neutrons or with a particular mass number, and noting that there can be other versions of that isotope. So an atom of an element with a particular mass number or number of neutrons. Now we need to be familiar with the different ways that we can notate different atoms. I included 4 very popular ways for notating atoms. My preference by far is this one, but I can't control which ones you'll see, and all 4 of these are possibilities. I'll help you break down what each piece of these symbols mean by filling in the following table. The first thing I decided to put in was the atomic number for each of these elements. In the first example, I recognized capital B, and that's boron, and if you didn't know that, you can check table S, but once you find capital B, you can look it up on the periodic table, and you can see a bold 5 beside it, giving you the atomic number 5. Nitrogen was written out as the full element name, but you can find on table S that its symbol is N. You can look that up on your periodic table, and the bold number, the atomic number, is 7. Carbon is 6, which we've talked about. You can use a similar method to look it up if you need to. And then Be, which you can look up on your periodic table, that's beryllium, and its atomic number is 4. The mass numbers that I just wrote in for each of these isotopes are taken directly from the notation example. So whenever we do a notation example, it seems like one thing that has to be included is the mass number. And the reason for that is because there are so many different versions of that element, there are so many isotopes, that one of the things we have to write down is which one exactly you're talking about. And that's going to be by indicating its mass number. So in the first example, obviously there's a 10 here, so I wrote in mass number of 10. Second example, 14, mass number 14. Third example, 12, so I put in a mass number of 12, and fourth example, a 9. So there's the mass number of 9. Now for the number of neutrons, remember it's just a short algebraic equation away. You just need to calculate it by subtracting the atomic number from the mass number. So in these examples, for boron 10, you just need to do 10 minus 5 is 5. For nitrogen 14, you can do 14 minus 7 is 7. For carbon 12, you can do 12 minus 6 is 6. And for beryllium 9, you can do 9 minus 4 is 5. So actually, both boron 10 and beryllium 9 happen to have the same number of neutrons. They both have 5 neutrons. And that's okay, by the way. They're allowed to have the same number of neutrons. Okay, so oxidation states you'll be able to find in the key on your reference table. And examples of oxidation states are just some just like integer numbers that can be positive or negative. Like, for instance, +1, -2, +3. Those are all examples of oxidation states. And oxidation states, they do have a complicated definition, but for now, what really matters for us is that we think of them as an overall charge of a particular atom. So this is not the charge of the nucleus, it's not the charge of the electrons, it's the charge of the whole atom, and that includes the protons and the electrons. So we take all of it together, and what would the charge of the atom be? Now, up until this point, we've thought of all atoms as being neutral, therefore their oxidation state would be 0. But we are going to study in the next few moments the possibility that an atom is not neutral, that an atom does have a charge. So the way that an atom can change its charge from neutral to some other number is if it gains or loses electrons. Now, atoms that have gained or lost electrons are termed ions. And now that we have a vocab term for ion, which is an atom that's gained or lost electrons, it brings up another important possibility, which is that if atoms can gain and lose electrons, how do we actually know how many electrons any given atom has? Because up until now, we've just been assuming all atoms are neutral, but now we're thinking maybe not all atoms are neutral. Maybe some atoms have gained and lost electrons. So there is a way to figure out the number of electrons that are in an ion, and I'll write it in next. So this is going to be a recurring theme in this year, and it's about what I've just written in. It says the loss of electrons is going to give you a positive ion, and the gain of electrons is going to give you a negative ion. This can be confusing for some, because a lot of us will look at a word like gain, and will think that the algebraic sign should be a positive one, but instead gain can mean negative, and loss can mean positive. And the reason is because of the identity of the electron itself. So since the electron itself is negative, then gaining one of those, gaining a negative charge, would make the atom, the overall atom, negative, making it a negative ion. And since the electron is negative, if you were to lose one, just like in math, when you subtract a negative, it's like adding. If you lose a negative, it would be the same thing as having a positive charge. So here are some examples of what I'm getting at. I put in 3 different isotopes. These are all carbon isotopes with a mass of 12 and an atomic number of 6. I wrote them 3 different ways on purpose. So I'm going to go ahead and write in the number of protons, because if it's carbon, it automatically has 6 protons. That's because the atomic number is always the same. Now, the number of electrons can vary from one atom to the next, and you can look at the oxidation state that's been given to figure out how many electrons the atom has. So here, for the first one, oxidation state of -4. So think of it in 2 steps. The negative is going to bring you up here, meaning that electrons have been gained, because gain of electrons will give you a negative ion. So if that's true, this negative ion must have gained electrons. So I'm going to go ahead and write in the word gain. And the trick is to think about how many electrons it must have gained. So since its oxidation state is -4, that means it gained 4 electrons. So in this particular table, it's a little bit unclear whether I was wanting you to write how many electrons were gained or lost, or whether I want the total number. But both questions are valid. So if I'm asking you how many have been gained or lost, in this particular example, we just figured it out. It was gained 4 because it was -4 as the oxidation state. But that isn't the total number of electrons. The total number of electrons is going to be the original number of electrons, and then you have to account for how it changed. In this case, it gained 4. So the original number of electrons is actually equal to the number of protons. So the original number was 6, and then it gained 4, which means that the total number of electrons in this particular atom is 10. I'm going to do a couple more examples for you. In the next example, we have an oxidation state of +2. And if the oxidation state is +2, that indicates that it is a positive ion, which means that it lost electrons. And if it's +2, that means it lost 2 electrons. So if they just want to know that, then you can stop your answer there and you can say it lost 2. But if they want to know the total number that this ion has, then you start with the original number, which is 6, equal to the number of protons, and you're going to need to subtract 2 from it because it lost 2. So 6, and it lost 2, so I'm going to say 4 electrons. So in the last example, it's going to be a +4, and positive means that you lost electrons, and 4 means that you lost 4 electrons, so I'll write that in. So that might be the whole answer, but if they want to know actually the total number of electrons that it has after losing 4, then just consider the original number, which was 6, and then subtract 4 from it, and you'll get 2. All right, so at this point, you have all the notes that you're going to need for this lesson. It's probably a lot. Again, I'm really sorry about that, but this was groundbreaking work. We're going to do this pair up in class tomorrow, so please go ahead now and in your classwork section of your binder, copy down this pair up, and you can even copy down the summary because both of these will happen during classwork tomorrow. And you can just put it right after the do now question in the classwork. Okay, so thank you very much. We'll go over this tomorrow. Don't forget, there is a quiz associated with this lesson, and we'll work on a homework as well.